Good morning. This is Nathiya, working as Assistant Professor in the Artificial Intelligence and Data Science Department from S.A.ENGG Engineering College. Today we are going to discuss a topic, AVL tree, which is in data structure and algorithm of GATE syllabus. Now we are going to see the AVL tree. Before we are going to see the AVL tree, we have to know what is tree data structure and binary search tree. Tree data structure, which is a hierarchical structure of the data, which is used to represent and organize the data in a hierarchical format, and it is a non-linear data. The data is stored which is not in a sequential manner. What is tree? Tree is a collection of nodes that are connected by edges and has a hierarchical relationship between the edges, and the topmost of the tree, which is a root node, and the leaf nodes below the nodes are called as a child nodes. This is the basic terminologies of the tree. Here this is a root node of the tree. The topmost node of the tree is the root node. Likewise, the below nodes, these are called the leaf nodes. Here the nodes which is connected between the two nodes is called as the edges, and the child nodes which have same parent, this child nodes is called as a siblings. And height of the tree is calculated from the down of the leaf nodes, which is the level 3 and the level 1, level 2, level 1 and level 0. So the height of the tree must be the tree. Next we are going to see about the binary search tree. Binary search tree is always stored in such a way that the values in the left subtree, which is less than the values of the root node, and the right subtree, which is greater than the root node. The condition for the binary search tree are left subtree, which is less than the root node, and the right subtree, which is greater than the root node. This is the representation of the binary search tree. Here the topmost node is 8. The first condition we have to check the left side. The values of the node is 3, which is less than the root node, so which is situated in the left side of the node. Likewise, here the value is 10, which is greater than the root node, so the node which is situated in the right side of the tree. This is the basic condition of the binary search tree. Next, why we are going for the AVL tree from binary search tree? The main disadvantage of the binary search tree is that all the elements are either greater or lesser, which is arranged in the one side, which means the tree becomes skewed. So the tree becomes slanted to the one side. To overcome the issues of the skewness, we are going for the balanced binary search tree. What is balanced binary search tree? Balanced binary search tree with m as the height of the left subtree and n as the height of the right subtree. If the value of the m minus s is equal to 0, either 0, 1 or minus 1, which is not greater than a 1 or which is not less than the minus 1. There are various types of the self-balancing binary search tree. These are the types of the balancing trees: AVL trees, red-black tree, B tree, B plus trees, play trees, and priority search trees. Here we are going to see about the AVL trees. AVL tree. AVL tree is defined as a self-balancing binary search tree. Here, where the difference between the height of the left and right subtree cannot be more than 1. That is, cannot be more than 1 and cannot be less than minus 1. This is the first condition, that the tree is kept to be a minimum. So, the searching and inserting and deleting nodes with the time complexity is O of log n. So the difference between the height of the left subtree and the right subtree should be the balance factor. Here the condition we have to see, the main condition is balancing factor. The condition of the balancing factor is the height of the left subtree minus height of the right subtree should not be more than 1, which means the value should be minus 1, 0 and 1. Here, this is the representation of the AVL tree. The first condition we have to see the binary search tree condition, which means the values which is less than the root node should be situated in the left side of the root node. The value which is greater than the root node, it should be kept on the right side. That is the first condition. Second one, we have to check the balance factor, which means the height of the tree. Here 0, 1, 2, 3. The height of the left subtree is 0. 0, 1, 2, 3, and likewise for right subtree 0, 1. We have to minus the height of the left subtree minus height of the right subtree. Like 3 minus 1, 2, 3 minus 2. The value should be 1. So it satisfies the condition. This is the AVL tree representation. Next we have to see the what is not AVL tree. Here is the which is not AVL tree. Likewise, here we have to check the, this is a balancing factor, sorry, height of the tree. Here 0, right subtree of the root node is 0, 1, 2, 3. This is the height of the right subtree. Likewise, we go for the left subtree. The height of the left subtree is 0, 1. If we subtract the minus left subtree, so the height of the left subtree is 1. Likewise, the height of the right subtree is 3. So 1 minus 3, we got minus 2, which is not satisfying the condition of balancing factor. Likewise, here we have to see the what AVL tree representation. Here the height of the left subtree is 2. Likewise, the height of the right subtree is 2. So 2 minus 2 is equal to 0. Here we are satisfying the condition of balancing factor. Likewise, we have to check which is satisfying the binary search tree condition, which is the value of the left subtree must be less than the root node. Likewise, the value of the right subtree value should be greater than the root node. Next, if suppose the tree which is not satisfying the balancing factor condition, we have to go for the rotations. In AVL tree, there are two main rotations, single rotations and double rotation. In single rotation, the left and right rotations are taking place. And likewise, double rotation, left right rotation and right left rotation, which is a double rotation. Like now we are going to see the what are the rotations one by one. First one, left rotation. Left rotation, when a node is added into the right subtree of the tree, it gets out of balance. We have to do a single left rotation. Like here we see the right subtree of the root node. Here the height of the tree is 0, 1, 2. Likewise, the height of the left subtree, which is 0. If you finding the balancing factor for this tree, so height of the left subtree is 0. Like minus, height of the right subtree is 2. The value of the balancing factor is minus 2. So which is not satisfying the condition of balancing factor. Here we have to do the left rotation, where the node of the left side should be transferred into the right side. So we are getting the image like this. That is A, B and C. Now we check the balancing factor for this tree. The height of the left subtree is 0. 1. Likewise, right subtree is 1. So now the balancing factor for this tree is 1 minus 1 is equal to 0. So which is satisfy the conditioning of the balancing tree. So this is for the left rotation. Next we are going to see the right notation in a single rotation. If the node is added to the left subtree of the tree, if the AVL tree may get out of balance, we do a single right rotation. Likewise, here the height of the right subtree is 0, 1, 2. Likewise, left subtree is 0. If you finding the balancing factor for this tree, it get out of the question. So now we have to rotate the right side, right single rotation. Now the tree is to be like this. So now we are checking the balancing factor of this left side, height of the left side should be 1 and like 1. So 1 minus 1 we get 0. So it is satisfying the balancing factor. Next we are going to see the double rotation. In the double rotation, first one left right rotation. Left right rotation is a combination in which first left rotation takes place, after that right rotation executes. Here we can see the example. Here the height of the left side, it should be here should be 2. On the right side we have 0. So first we have to make the left rotation. So now the tree is to be like this. Again we have to perform the right rotation. Now the tree has to come. Now we check the balancing factor for this tree. The height of the left subtree is 1. Likewise right 1, 1 minus 1 0. So we satisfy the balancing factor. Likewise for the right left rotation. Here the right left rotation is a combination in which first right rotation takes place, after that left rotation execute. So the tree is to be like that before a rotation. First we have to perform the right rotation. Now the tree has to become here like this, and again we have to perform the left rotation. Finally we got the tree like this. So now we are going to check the balancing factor for this tree. We get the 0. So now these also satisfying the condition. Now see the operations. What are the operations which takes place in the AVL tree? There are basically main operations are the three operations: insertion, deletion, and binary searching. Now we are going to see the insertion. While inserting the element, we have to first check the binary search tree condition. So by inserting an element in the AVL tree, we need to find the location particular element that needs to be inserted. Then the element is attached, the same as in the insertion is binary search tree. Like we have to go and see the example for the insertion tree. So here the tree, we have to insert a key 3 in a tree. We know that the condition for the binary search tree is the value which is less than the root node, we have to insert that node in the left side. If the value is greater than that node, we have to insert the key in the right side. Now we are going to insert the key 3. Here first we are going to check the condition. If 3 is less than root node or a greater than root node, which is less than, so move to the left side of the tree. Again we are get to check the values in the next node. Here the node is value 5. Here we are going to check the node, the value is 3, which is less than the node 5. So now again we are going to move to the left side. Now check with the node 2. Here the value of the insert, the key of the node which is going to be inserted, it is greater than the 2. So we are going to insert the node here, which means the node has to be inserted here with the key value 3. After inserting the node, the tree should be like this. The tree has to be inserted here. If after inserting the node, we have to check the condition balancing factor like this. So if the balancing factor of the left side node 0, 1, 2, 3. So to check the balancing factor of this tree node, the height of the left subtree is 3. Likewise, right subtree is 3. We get the value 0, which satisfies the balancing factor. Now we have to insert again the another node, which is insert 33. First we have to check the condition of the binary search tree, the value of the key which is going to be inserted, which is greater than or less than the root node. 33, which is a greater than the root node. So we have to move to the right side. Next again we are going to check with another node. Here the node is 50. We have to again check with the node. So the value of 33 which is greater than the 50. So again we have to check the condition. Finally we have the node, insert node here. That is, after inserting the node, the tree should be like this. Now we have to check this balancing factor for this tree, but the balancing factor of the tree is greater than 1. So we have to perform the rotation. Here we are going to rotate the right side rotation. After rotation, the tree will be like this. So now we are going to check the balancing factor for this tree. The balancing factor for left side, the height of the left side node is 3. Likewise, the right side node is 3. Now to check the condition, balancing factor is height of the left subtree minus height of the right subtree, which is 0. It satisfies the condition. So next, this is the insertion operation. Next we are going to see the deletion operation. Deleting an element in AVL tree also comprises searching an element in the tree and then deleting it. So first we have to search the element where it is and finding the deletion. So now see the example for the deletion. Here the tree is there. From there we have to delete the tree with the key values of 17. So where it's to be, first you have to find the value is 17, which is greater than the root node. So search in the right side of the node. We have find out the node here. That the node which is to be deleted is here. After deleting this node, the tree will be like this. Now we have to check the balancing factor, if it has satisfied the condition or not. It satisfies the, now see the condition, satisfies the condition. Now, but here 1, 2. So after deletion, we have to perform the single rotation on this node. Now we are getting the balancing factor which satisfies the condition, balancing factor here. Next the operation is searching. The elements, read the element provided by the user X says, compare the root element. If it is same, then find out. If the X is less than the root element, we have to find in the left side of the row. If the X element is greater than the root node, we have to searching in the right side of the node. This is an example. For example, we have to search an element 20 in the provided tree. Here the root node is 10. we have to check with the root node whether 20 is greater than or less than the root node. Is it greater than the root node? So move to the first node. Here 15, we have to find out the node which is 20. So which is greater than the 15? So we have to again move this here. So we find out the elements of the 20. So next, these are the basics operations of the AVL tree. Here we are going to see what are the applications we are going to use in the AVL tree and the advantages and disadvantages. First, application. It is used to index huge records in a database and also to efficiently search in that. For all types of memory collection, we are going to use the AVL tree, and for the database application also we are going to use a AVL tree. And the software, lastly we have to apply it in a corporate areas and storyline. Like this, we have many real-time application we can use by using the AVL tree. Then advantages of the AVL tree. AVL tree can self-balance to themselves. It's surely not skewed because we are applying rotations. So it's surely not skewed. It provides faster lookups than red-black tree. When compared to the red-black tree, it provides a faster lookups. And height cannot be exceed log n because n is the total number of the nodes. Because how many nodes is there? The height should be within the nodes. It does not exceed the nodes. So that means the height of the exit does not exceed the log n. Then the disadvantage of the AVL tree are it is very difficult to implement and it has high constant factors for some of the operations and less used compared to red-black trees. Due to its rather strict balance, AVL tree provides complicated insertion and removal operations as more as rotation as performed. And also it takes more processing for balancing. These are the advantages of the. Let's see an example. Construct an AVL tree by inserting numbers from 1 to 5. First we have started with digit 1. So 1 is a root node. Now we have to checking the balancing factor which is 0. Next we are going to insert the node 2 which is greater than the root node. So it should be situated on the right side of the node. So again next element we are going to add is 3. Which is again check with the condition. First root node which is greater than the 1, move to the right side of the node. Again check with the next node which is greater than the 2, then which is situated in the right side of the 2. So now we are checking the balancing factor here. The left subtree node is 0 and the right side of the root node should be 2. The height of the left subtree is 0 and the right of the right subtree is 2. So when you are finding the balancing factor, it should be a -2. So we have to perform the rotation. Now we are getting the tree like this. So now we are going to check the balancing factor for this tree. It should be a 0. Next we are going to add the element of insert element 4. Likewise we have to check with the root node if it is greater than or less than the root node. If it is greater than, we have to keep the node in the right side of the node. If it is, and furtherly check the balancing factor of this node. Finally we have to add the node insert 5. So 5 is added in here. Now checking whether the tree is imbalanced or balanced. Again perform the rotation. After rotation the tree will be like this. Finally find out the balancing factor for this tree. If it is satisfy the condition, that should be like this. So now we are going to see the last year gate example. So previous question, consider the following AVL tree. Here the tree is given. Which of the following is updated AVL tree after insertion of 17? The given tree is here. We have to insert 17. After the insertion of tree, the tree will be like, which is here the options are there. The solution is to be derived here. First step 1, the element is first insertion in the same way as a binary search tree. Therefore, after insertion of 70, the binary search tree can be shown like this. Next, however, balance factor is disturbed because we have checked the balancing factor there. It's disturbed, requiring right-left rotation. To remove the right-left rotation, it is first converted into the OR rotation. So after conversion of the OR rotation, the tree is like to be this. After removal of OR rotation, AVL tree is generated, which is like this. If we find the balancing factor for this tree, here the height of the left side is 2, likewise the right side is 2. Now the condition is 0, which is satisfy the balancing tree. So the option for this question is C. So the answer for the question is option C. Thank you. Let's see in the next video.